Okay, so in this particular video, we'll look at a composite wall problem to understand the series parallel arrangement and how to draw the circuit diagram in this particular scenario. So we won't take any values or and like get a number answer, but we'll just look at formulating the math, like creating a mathematical formula for this problem and then drawing an appropriate circuit diagram. So let's dive into the problem. So let's say we have a composite wall, which is like a combination of four materials A, B, C, and D, and they have a different thermal conductivities, aka Kb, Kc, and Kd. Now we will assume that this is a one directional heat transfer, so heat is just flowing in, let's say, the x direction, and this is your x direction, and the block in between is divided into two, so you have Kb and Kc, uh, which compose the block in between. So, and there is heat transfer due to radiation on the left surface, so surrounding is at T infinity 1, surface is at T1, and there's heat transfer due to radiation, whereas on the right surface you have heat transfer due to convection. The surface temperature is T2 and the surrounding temperature is T infinity 2. Now, the first thing that you do whenever you look at such problems is that you must write down your assumptions. So even if you see a similar problem or whenever you solve a heat transfer problem, and even for your exams, if I ask you any if I ask you to solve any such problem, the first thing that you must do is you must write down assumptions. So we will do that. So let's write down the assumptions. What is our first assumption? Our first assumption is that we just have heat flowing in one direction. So we'll assume, and there's no information given about heat exchange between block B and C. So we don't have any information about that. So let's say that phase between B and C is insulated. Okay, that's our first assumption. Our second assumption is that our heat is flowing in x direction only. Our third assumption is assume that all properties are constant. So let's say this is, we have an H here. So all the thermal conductivities and the heat transfer coefficients are constant and are not a function of any of the quantities like temperature or time. So let's say we have constant thermal properties, and our fourth assumption is that the system is in a steady state. So we have steady state conditions, I'm sorry. So these are the four assumptions that we'll have. Now we need to make a circuit diagram for this. And what is the first thing that we'll do? The first thing that we'll do is we will define we will draw the temperatures at the two extremes. So let's assume, because the heat is flowing in the positive x direction, this will mean that T infinity 1 is greater than T infinity 2, and the heat is flowing from hot to cold, right? So let's say this is T infinity 1, and let's say this is T infinity 2. Now we know the temperature of the surfaces. So let's say this is T1, and let's say this is T2. Now we don't know the surface temperatures at these interfaces here, so we won't plot that, but let's make the resistances. So let's say the resistance between T infinity 1 and T1 is due to radiation, so I will call it as R rad. We have a temp we have a resistance between due to block A, so that's due to conduction, and we know that the resistance due to conduction will be the length of block A into the thermal conductivity of block A into the area of block A. After this, the most important thing is that we have two resistances, and the resistance offered by block B and C are in parallel. So we will draw them in parallel, right? So the resistance due to B is again it's due to conduction, so it will be length of B into conductivity of B and area of B. Similarly for C, and then we have the resistance due to block D in series with B and C. So we have this right here, and then we have the resistance due to convection, right? So the first step after uh, you look and read the problem is writing down the assumptions and then drawing the circuit diagram and making sure that you have included all the resistances that are stated in the problem. If say the problem says that there is insulation on one surface, you may not like you may not have one of the resistances, or maybe none of these resistances due to radiation or convection. So you can have a problem where it just says that you just have a composite wall and there's just heat transfer due to conduction. So you'll just have resistance due to A, B, C, and D, and you won't have resistance due to conduction and radiation in that scenario. So um, be careful while you read your problem and identify how many and what kind of resistances you have. So here we know what the resistance due to conduction is. We know what the resistance due to convection is. This will be basically your 1 upon H into AD. So that will be your resistance due to convection, but we don't know uh, how to represent your resistance due to radiation. So what is R rad? So let's look at it, or let's derive a formula for it. So by Ohm's law, R rad will be delta T upon Q rad. Okay, our Q radiation will be epsilon into sigma into T infinity to the power 4 minus T1 to the power 4, right? I can write this as epsilon sigma into, I'm expanding t infinity to the power 4 minus t1 to the power 4, and I'm writing it down as t infinity 1 square minus t1 square into t infinity square plus t1 square. So if you multiply this, you'll get the fourth power of t infinity 1 and fourth power of t infinity minus fourth power of t infinity 1. So I can further expand this bracket right here and write it down as epsilon sigma into t infinity plus t1 into t infinity 1 minus t1 into t infinity square plus t1 square. Okay, so this right here is our delta t, and what we'll do is that we'll define a radiative heat transfer coefficient. That's heat transfer coefficient due to radiation, and we'll use the remaining terms to define that. So if this is our delta t, the combination of these terms will be our hr, which is epsilon into sigma into t infinity 1 plus t1 into t infinity 1 square plus t1 square. So basically your hr here will be a function of your temperatures, T infinity and your surface temperature. So if you get a numerical problem, you'll have a T infinity given, you'll have the surface temperature given, you'll be given information about if the body is a black body or if it's a gray body, what's the emissivity of the body. Sigma is a constant, so you know the value for that, and you will be able to find the value of HR. So our resistance due to radiation will now simply be 1 upon HR into A. So this is how you represent your resistance due to radiation. And let's say this is equation 1. Now we still have our RB and RC in parallel. So we need to find what's the equivalent resistance for that. So because our RB and RC are in parallel, our equivalent parallel resistance, say PAR, will be 1 upon RB plus 1 upon RC. So when you have two resistances in parallel, the equivalent resistance is not a simple addition, but you can write your 1 upon equivalent resistance equals to 1 upon resistance 1 plus 1 upon resistance 2. In this case, it will be B and C. And let's substitute the values here. So it will be LB upon KB into AB plus 1 upon LC divided by KCAC, or let's write this down as KBAB upon LB plus KCAC upon LC. Now for simplicity, let's say LB is equal to LC, and let's say AA is equal to sorry, AB is equal to AC. So our parallel resistance or equivalent parallel resistance will be, say, AB upon LB into KB plus KC. Okay, so that's our equation 2. Now we've reduced or found out the equivalent parallel resistance. We can redraw the circuit diagram as T infinity 2, and then okay, this is T1, this is T2, this will be 1 upon HR into AA, this will be LA by KA AA, and this right here will be the R parallel that we just found. This will be LD by KD AD, and this is 1 upon H by AD. Okay, so now we don't have any parallel resistances in the new circuit diagram that we have, and all of them are in series. And because all of them are in series, we can find out the total resistance, which will be the summation of all the resistances. That's the R rad plus R A plus R parallel plus R D plus R convection, right? And for simplicity, let's assume that all the lengths are equal. Okay, so thickness of all the composite materials are equal. If you get a numerical problem, these lengths will be given to you, and let's say that the area of B is equal to the area of C, which is half the area of A, or I'll just uh, say the area of A is A. Okay, so after writing these assumptions, our R total will be 1 upon HR into A plus L by KAAA plus L upon A by 2 into, oh, I'm sorry, into KB plus KC plus L upon KD into A plus 1 upon HA. Or if we take all the areas in common, our R total will be 1 upon A multiplied by 1 upon HR plus L. Let's take, yeah, L by KA plus 2L by KA plus KB plus KC plus L by KD and plus 1 upon H. So this will be your total thermal resistance between T infinity 2 and T infinity 1. And if you need to find the heat transfer rate, it will simply be Qx equal to T infinity 1 minus T infinity 2 upon R total, and that's it. So what are the few important things that we need to note? So you must note that you should identify uh, if the resistance are in series or parallel, and draw the correct circuit diagram. So second thing is draw the correct circuit diagram. Okay, so please go through this video properly. I have solved this problem using generalized notations, as in K's, L's, and A's. But if you get a numerical problem, you will be given the values for the thermal properties or the dimensions of the composite blocks. So you should be able to use them properly and get a value for the heat transfer rate. So when we have a composite system, sometimes it's convenient to define something called as a overall heat transfer coefficient. It's denoted by uppercase U. So the problem might give you an overall heat transfer coefficient instead of giving you individual thermal properties of each composite material that's part of the system. So it will just say that, okay, the overall heat transfer coefficient of the entire system is so and so, and find the heat flowing across the system if the endpoint temperatures are T1 and T2, something like that. Okay, so what is the definition of the overall heat transfer coefficient? So if you remember, for the composite system that we just solved, our Qx was delta T upon R total, right? So we defined U as 1 upon R total into A, right? So this, and we use Newton's law of cooling. We use Newton's law of cooling and say that Qx is equal to U times A times delta T. Okay, so you might get a problem where you have U given, you know the delta T, and you might have to find what the heat transfer rate is. Or the other scenario can be that you are given a composite system and you need to find what U is, and for that you will have to find what R total is. Okay, and we just looked at how to find R total uh, in the problem that we just solved. So keep this in mind. uh, Read through the textbook, read chapter 3, and read what overall heat transfer coefficient is, and we will also be using this in some of our problems, so you will be able to understand this concept in more detail. Now another thing that we ignored in our composite system, or have been ignoring until now, is something called as a contact resistance. So say you have a composite system, or if you have, say you have two materials. Okay, say this is material A and this is material B. Okay, say this is A and this is B, and that's the interface of the material. And let's say we have a heat flux flowing in X direction, in this direction right here. So this interface does not have a perfect contact. Okay, you might have some uh, rough edges or gaps or some imperfections between the interface or in between the contact of the two surfaces, and due to that contact, so for contact resistance, let's define it formally. So for contact resistance, there may be a temperature difference across the interface between the two materials. Okay, so there will be some delta T. So let's say uh, the temperature at this interface is TA and the temperature here is TB. Okay, and let's say we have a thermal gradient like this here and like this here, and that's our delta T. Okay, so there will be some heat flowing through this contact. Let's say it's Q contact, and this will be mostly due to conduction, and there will be some heat flowing through the gap. So let's say this is heat flux through the gap. Now this will uh, be due to convection or the air gaps between the surfaces. So if we have something like this in a composite material, and if the value of thermal resistance is given or it's need to be found out, and if the problem says that the two interfaces that you have are not at the same temperature, they have a certain temperature drop or temperature difference between them, that means that some finite amount of thermal resistance exists and you cannot ignore that. So that delta T that we have is attributed to thermal resistance, and let's say we denote that thermal resistance as RTC, so the resistance thermal due to contact, and in this case it will be TA minus TB upon the heat flowing across it. Okay, and why do we have this temperature drop? The two reasons are surface roughness. So due to the surface roughness, there might be like both the surfaces might be uneven, and due to the unevenness they will not be perfectly matching. So you will never have a perfectly smooth plane surface. Each surface will always have some surface roughness, and due to those surface roughness you may have small gaps in between, and these gaps will mostly be air filled. Okay, so this is an important concept as well, contact resistance. Again, read the problem that you're given. If your interface is not at the same temperature for both the composite materials, say your interface right here has two different temperatures TA and TB, that means a finite contact resistance exists. So you might either be given the value of that contact resistance, or you can find it from a source, and then you'll have to uh, use it in while finding the overall heat transfer coefficient or the total resistance and you will also have to mention it or draw it in your circuit diagram. So we will be looking at one problem where we might include thermal resistances or thermal resistance and draw a circuit diagram accordingly.